all the wonderful talks so far. I know it's towards the end of the week and people are probably getting tired. And apologies that my talk is on a slightly different topic. So there aren't any, at least imminent, shuffle algebras within it. But if you can find some, that would be great. Please let me know. I will mainly talk about quantum groups, however, associated to a symmetrizable Kac-Moody algebra. And I'll talk about two different categorical braid group actions. And if anything, hopefully this serves as motivation to look at the categorical setting for quantum affine algebra as one aspect of this. So I'll talk about one project which is already published, which is joined with and towards the end of my talk, I'll also discuss work in progress, which is with my PhD student, Erica Becerra. But I think I will start by outlining at least the ideas of the two projects. So if I run out of time, you will have seen the punchline at the beginning already. I won't keep you in suspense. All right, and as I mentioned, let's assume that G is a symmetrizable Kac-Moody algebra. At some point, for simplicity, I might assume semi-simple. And at some point, we will have to assume that it's simply laced, and I'll let you know when we need that particular assumption. But it is, what I'm about to tell you is expected to hold in full generality. It's just some of the results are only available for simply laced type for now because they've been obtained through geometric means. So let I denote the Dickin diagram. And so alpha I are the simple roots. I check are the simple codes. And I might need some more notation and I'll introduce it as I go along. But let me introduce one more thing for now. So capital lambda I'll denote as the weight lattice. And generally the representations we're going to work with here are so I will use UQGREF to denote, so I hope this is not misleading, but so they're going to be, highest weight integrable representations. So in particular, with the highest weight lambda, which is a dominant integral weight. And their tensor products and so on. So this is the type of representations we'll be interested in. So let me start with the two types of braid group actions. So two incarnations of the braid group. And lucky for me, the mini courses have already covered have discussed both of them to some extent. So here's the first version, which I'll call Lustig's action that Sasha Cymbaluk already discussed in his mini course. So if we start with this, maybe let me start a little bit lower, collection of representations, then, so as we saw earlier in the week, and I'll just use single initials for the sake of time, but so L here stands for Lustig, told us that there's a action of the braid group of type G, on any individual such representation. So let me write it as follows. So the braid group of type G acts on any quantum group representation like that. I'll use the fact that this was already discussed to some extent, but if you want the formula, I'm happy to share it, perhaps a little bit later. And so the categorical version of this, let me use a different color, is as follows. Oh, this is maybe not the best color. If blue is visible. It's also not good. Orange. Maybe I'll stick to white. Sorry.
You have some there.
Oh, there, I think they were, got a little bit.
Yellow.
Oh, thanks. Okay, great, these are. Perfect, thank you. So categorical and so UPG representations. So they were originally constructed, let me put it over here, by Chuang and Ruquier. As I mentioned, I'll only use initials just for the sake of time. And Kovanov and Lauda. So there's been two different constructions, but work of Brandon and Cottis Lauda giving the proper citation showed that in fact they agree with each other. And so there's a categorical higher level version of these representations. And there's also a categorical version of the braid group. So using so-called Ricard complexes. And so these were constructed by Chuang and Ruquier, mainly in the context of actually studying the representation theory of the symmetric group in positive characteristics. And they used it to prove the so-called Breuil's abelian defect conjecture. So that's where they originated, but they turned out to be very handy in the representation theory of quantum groups. And Cottis and Kamnitzer showed that they do satisfy the braid relations, but they used a geometric version of categorification. So using derived categories of coherent sheaves. So this is only known in type ADE, but it's expected to be true in general. And what I'm going to talk about today, though, is algebraic categorification. So both of these are from an algebraic perspective. And so this gives us a categorical braid group action. Through these Ricard complexes. And again, that recovers the usual one through the Grothendieck. And I won't talk as much about what I'm going to write next, but let me mention it just for part of the motivation here. So there is so I should have also said that Q here is generic, so not a root of unity throughout. So one can consider the limit as Q goes to 0, and so in work of Kashiwara and Lustig, obtain G crystals, which are certain combinatorial shadows of the representations. And they also carry some type of symmetries, just like these quantum Weyl group symmetries on the level of the representation. The crystal carries an action of a cousin of the braid group called the cactus group. And in principle, one could go from the braid group action to the cactus group action here. So what our first project was about is understanding the structure of some of these braiding functors for particular types of braids, namely the ones corresponding to half twists. So maybe let me put another sign over here. And so this type of property, so part of the motivation to study it is that it recovers the cactus group action from the categorical perspective. But I'm only going to talk about the top two rows. I'm just giving you the bottom one for some motivation of why we were interested. One reason we were interested in this. But so in joint work with Losev and Jacobi, we showed that so the braiding functors, let me call them theta, W naught P. So this is the longest parabolic Vog group element. Or more intuitively, you can think of them as the half twist braiding functors. Have the structure of what is known as a perverse equivalence, and that I will explain in more detail later in the talk. So, are perverse equivalences. Maybe just not to keep you in the dark completely, the general intuitive idea is that there's some filtration on the category, and they're upper triangularizable with respect to this filtration, as well as there are some additional nice properties there. So this is the main property that we're interested in for this family of braiding functors. So where P is a parabolic. Okay. So this is the first story. And now the second one is, well, after we completed that, we decided to think about other braid group actions. So can we observe the same property in other circumstances? And as I mentioned, one of the upshots of having this particular type of property is that they allowed us to recover this action on the level of crystals as well. So for version 2, I want to think about sort of tensor products. And there we have the R matrix acting, giving us a braided monoidal category structure. So one has the same, well, analogous story. So we can think about these representations. And the n-strand braid group action, acting on n-fold tensor products. So, and by acting, I mean it really permutes the tensor factors. So it doesn't, maybe I should put this in quotation because it's permuting the factors. And then there's the categorical version of that as well. Now the key structure we're interested in here is the tensor product. And so the categorification there is due to Webster. So categorified tensor product. So Ben Webster used certain finite dimensional algebras called KLRW algebras to realize the categorification of a tensor product of irreducible highest weight representations with dominant integral highest weights. So, and I should also mention work of Loseb-Webster, which showed that this particular instance of a categorification is essentially the unique one that one can have. And then we also have an action of the braid group. So again, due to Webster, this is a categorical and braid action. And again, we can recover back the classical story by taking the Rotten group. And again, our motivation for, so this is the, sorry, I should say this is the, we're using the R matrix. And on the categorical level, this is realized by, so in the first instance, it was through the action of these Ricard complexes, and here it's tensor with a certain line module. Maybe I'll call it VI, which is a particular kind of line module, and hopefully we'll get to discuss that in some more detail. And so part of the motivation of thinking about this braid group action is again to recover some information on the crystal level. So just as these representations form a monoidal category, crystals are also a monoidal category, but it has a structure of a boundary category. So the commuter is not an R matrix, but something of a slightly different nature, which produces an action of the N cactus group. And let me put co-boundary category structure here. And this is due to Enriquez and Kamitzer. And again, in principle, one can recover that from the braid group action here, but perhaps a more interesting way is to look at the, again, the family of half-twist braiding functors. And now this is just on the usual braid group on N strands, whereas before we had the braid group matching the type of Kac-Moody algebra we have. And our goal, so this work in progress with Erica, is to show that these are also perverse equivalences. And following then the same recipe, that would allow us to recover the action of the cactus group. But as I mentioned, now I'll primarily focus on, for each of these diagrams, the top two rows in version 1 and in version 2. Any questions so far? Yeah?
Can I just double check, this Lustig action is like this triple exponential formula?
Yeah,
okay.
EI to some divided power FI, yeah, exactly.
By perverse equivalence, you just mean that there is some heart in the category?
Yes, I was planning to define it if, time permitting, but exactly.
It's not the usual like perverse filtration which exists in like when you take the constructible category.
No, it's I mean in terms of in the setting of triangulated categories and hearts. T structures and hearts, but I'll give more details on that, yes. So it's more algebraically based, yeah.
Do you expect like more general non-developments, like also like is this perverse equivalence property, like do you expect it to hold more general?
Yeah, so at least in the first instance, this was generalized by, I'm blanking on the name, but I think it's Gosso and Jacobi. And they generalized the type of value elements that, so they characterize precisely the ones, so there's a more general family for which this is true. So these particular ones recover the cactus action, but
Yeah, they generate, okay.
yeah. questions. Okay, so have people here seen categorification before? I want to start with SL2. Is that okay? Let me start with SL2 as the warm-up situation. So categorical G and UPG actions. So as I mentioned, this was developed in the work of Chuang and Rutia and Kovanov and Lauda. It does involve a lot of diagrammatics, so I think I'm going to sweep those mostly under the rug, but I'll show you some of the SL2 picture. So, as the warm-up, let me start with D equals to SL2. And so there we have our three elements, E, H, and F, acting on some integrable representation. And one of the crucial relations here is EF minus FE restricted to the nth weight space is just n times the identity. And so not too remarkable on the classical level, but when we look at the categorical version, this is where this relation gives us some further interesting information. So how is that constructed? So this representation gets replaced by an abelian category. Where each of these components decategorifies to the corresponding weight space. And we have exact functors E and F, replacing the Chevrolet elements of the Lie algebra. So they act on C. And so moreover, they're bi-adjoint. And so we have the unit and co-unit of their adjunction. And they produce natural transformations. So from 1 to FE and from EF to 1. So these are the unit and co-unit of bi-adjunction. We have two further natural transformations, and ultimately all of these together are used to construct a natural isomorphism corresponding to this relation. So let me call the other two X and T. So which realize so let me give it for n greater than or equal to 0, and similarly for n smaller than 0. A natural isomorphism, so I'll write it as EF, restricted to the n weight category to, is isomorphic to FE restricted there, plus some copies of the identity. So this is one of the upshots. So that equality is no longer an equality, but an isomorphism, a natural isomorphism. Notice in categorification, we prefer not to work too much with minus sign whenever we can help it. So that's why this can be one way to realize it is to rewrite it this way. Because once minus signs are unavoidable, then you have to start working with complexes rather than just the underlying category. But in this case, we can avoid the minus sign. And a further upshot is that X and T give an action of the nil affine Hecke algebra on n strands on powers of E. And this is where the diagrammatics is hiding. So this is the categorical version of such an integrable SL2 representation. And so, for instance, if we take the adjoint SL2 representation, then we have three weight subcategories, and they're just realized as complex vector spaces on the two ends, and then modules over the ring Cx mod x squared. So this is one realization of such a categorical representation. And then the E and F functors are just induction and restriction. Sorry, this is induction and restriction. Okay, so then more generally, what's that?
What is X and D here? Like.
Oh, yeah, I think I can. That's a great question. I can write it down, but maybe let me tell you afterwards. Yeah, that's a great question. I'll give you some more information about this example, but not specifically X and D here. Yeah. So more generally, if we're working with so notice here, I'm not talking about quantum here yet. We're just talking about the Lie algebra G. And the categorification looks fairly similar when we work with the quantum setting, but we have to introduce grading to account for the quantum parameter. So let me continue talking about the non-quantum case, and then I'll say briefly the quantum modification as well. So we want a strict, so where a junction and units are, so a category which is strictly associative and unital. And well, we need a few more adjectives, although we won't use them very extensively. So additive and K-linear, where K is any field, doesn't have to be algebraically closed or characteristic 0. Two category, I'll call it curly U, categorifies, so categorifying. So we take the universal enveloping algebra, but because we want to in particular isolate the individual weight spaces, we take the Lustig idempotented form of that, and that is what is really getting categorified. Where we add all of the idempotents which are projecting onto individual weight spaces. So this category has objects are just elements of the weight lattice. And then one morphisms are generated by the EIs and FIs. So EI goes from lambda to lambda plus alpha I, and FI goes from lambda to lambda minus alpha I. And again I'm not writing down all the idempotents we really need here by restricting to lambda, the lambda weight space, as well as two morphisms. And in the previous instance, so we had the adjunctions, the unit and co-unit, and x and t, and those are what is realized diagrammatically. So xi here can be drawn as a diagram with a dot, which goes from ei to ei. Then we have tij, which you can think of as a crossing, going from ei ej to ej ei. And then we also have cups and caps. So ei fi to the identity, and the cap, which goes from the identity to fi ei. Okay, and again, these are generated by. And we also need, well, everything with the direction swapped and the e's and f's interchanged. So direction swapped. Okay, so this is the more general version of a categorical representation. And then, well, we need a lot of relations to really capture the underlying representation theory. I will not subject you to all of those, but maybe let me just say these are the, well, diagrammatic relations capturing the representation theory. Maybe I'll draw one just to illustrate what is happening. So subject to KLR plus further, so Kovanov-Lauder-Ruchia and further relations. But for instance, one type of relation is if you have a diagram like this, so, you know, two things happening locally, a crossing and a dot, then you can slide past, but at the cost of also adding the identity. And so, again, these are the type of relations that are required from the viewpoint of the representation theory. And then categorical representation, and again, I'll be slightly vague here, is a two-functor from this two-category U to an appropriately selected two-category K. And as I mentioned, for the quantum setting, we need to introduce grading as well. So a graded version, let me call it curly U sub Q. I'll omit the G to indicate this is the categorical version. So categorifies. So again, we want the integral idempotented form of the quantum group. So this is generated by the divided powers of EI and FI. And we've also adjoined all the idempotent projections to the weight space.
Sorry, so X and T, they are supposed to be elements of Lustig's braid group. Could you verify the elements of Lustig's braid group?
Oh, sorry, not quite. So not yet. I haven't introduced the braid group action yet. Yeah. So X and T. So here in the Nil-Hecke setting, for instance, oh yeah, maybe I can say, yeah, so T acts on, you know, in this situation in position I and I plus 1. And so they braid with each other, but they square to 0. So
It's a quotient of the braid group by
yes. But this is not the braid group I was talking about. Yes. So the X here is like a polynomial ring. All the places where X can act, they all commute with each other. The TIs are a quotient, but yeah. So certainly those are some types of relations we can have. Any other questions?
So this U cube will G generated basic dividing powers?
Yes, that's right.
So you consider this as algebra of
ZQQ inverse.
Okay, so you take variables integrality.
Yes, exactly. But then when we take the Grothendieck group, we tensor tensor with CQ to recover the, yeah. So that's not a problem. Okay, but now I'm going to actually tell you about the braid group that we're interested in. Oh, and I haven't erased the picture yet. So now I'm about to explain a little bit more how one gets these Ricard complexes and gets the categorical braid group action through them. All right. So again, let me start with the SL2 story. So this is, I think, now part 3. So as I mentioned, they were constructed by Chuang and Ruquier. And so for the SL2 picture, we can start by considering the following reflection matrix, which is can be written as the exponential of minus f, exponential of e, exponential of f. So this, strictly speaking, lives in the group SL2. And if we want to write it as a general expression, it's going to be some infinite sum with a triple product. But if we specialize to weight spaces, then, so S restricts to an isomorphism on the weight spaces in particular. I'm using the same notation as before. So Vn here is the weight space of some integrable representation. And let me use minus n, just for notation purposes later on. And then it has a relatively straightforward expression where you just need to use a single, so just one E and F in the following way. So when trying to categorify this, as I mentioned, one problem is that now we have minus signs. So rather than a functor on the original category, what we'll need is a functor which maps from complexes on this category to complexes. So this is how one can deal with the minus sign. So consider the complex of functors. Let me call it theta, which again we can write as in terms of different components corresponding to the weight. And each theta n is itself a complex where in each component we have a functor. So, and the underlined part is the homological degree 0 part. So we have a version of divided power at this level as well. And so n plus 1 f1, e n plus 2 f2, and so on. So it goes down infinitely. And so this gives us a functor, as I mentioned, from complexes with entries, the objects from the weight category C minus n to complexes with entries, the objects from Cn. And furthermore, this is what's going to ultimately decategorify to this reflection matrix S and produce the braid group action here. Maybe just to say a little bit the ingredients for how does one construct this complex. So first we have the divided powers of E and F, and those are obtained using the nil affine Hecke action. So this is one of the ingredients for producing theta. So En and Fn, divided power, are obtained via the nil affine Hecke action. And the differential is obtained from adjunction. Let me just maybe write one instance. So from the unit and co-unit operations. So this is -1. So via adjunction. This is how one can construct theta in the SL2 instance. And so one of the theorems of Chilani-Murukine is that theta induces an equivalence on the bounded derived category of C, of our abelian category C. So on DBC, that restricts appropriately to the weight subcategories. So DBC minus n to DBCn. And decategorified, maybe I'll just write square brackets to indicate that, to the original operator S. When we take Grothendieck groups. Okay, so this produces a braid group. So the categorical version of the Lustig braid group action, which I already erased the diagram. But so in the case of SL2, and maybe just to, again to continue the example from the adjoint representation. So, and as I mentioned, mostly I'm going to be working with, so notice I'm not talking about any grading here. One can talk about the quantum setting by introducing grading appropriately, but the formulas become a little bit less fast to write down. So maybe for now I'll just stick to the non-quantum language, but one can equally well include the grading. So if we take this ring, whose representations are giving us a categorification of the zero weight subcategory, and let's take n to be an R mod. Remember, this was one way to realize C0. Then this functor acting on the zero weight component, so dB R mod to dB R mod. Takes, so in principle I need to tell you what happens on the whole complex here, but let me just, for simplicity, just take one element in our modules, and it's going to produce a two-term complex where, so in homological degree 0 we have n, in degree -1 we have R tensor n, and then the differential is just the action of R on n. So this is maybe relatively easy to check in the SL2 setting. Okay, so then again this can be generalized to, well, arbitrary symmetrizable Kac-Moody, and then we have one of these functors for each element of the Dinkin diagram. So more generally, if we take C, so a categorical UQG representation, and let's take an element of the weight lattice and an element of the Dinkin diagram, then we get a functor theta I, which goes from dBc mu, so from the bounded derived category of the mu weight category to changing the weight by SI here. And again, this gives us an equivalence. And so these have been constructed in complete generality for G, as I mentioned, symmetrizable Kac-Moody, and C, categorifying any highest weight irreducible representation of dominant integral highest weight. Now, the fact that they satisfy the braid relations, as I mentioned a little bit earlier, this is only known in the simply laced case because this is proved geometrically. So this is work of Cottis and Kamnitzer, who proved that, so theta I satisfy the braid relations. So, this is only known for G of type ADE, or simply laced. So then we just have two types of relations. They commute when the two nodes are not connected in the Dinkin diagram, and then we have this three-term relation if they are connected. So we know that the braid relations are satisfied, but one thing that still hasn't been done and is an open problem is actually checking that this is a strong braid group action, namely that these isomorphisms are canonical. So for now, we only know that this produces a weak action, but for our purposes, this is enough. So in particular, then, we can take an arbitrary element of the Weil group, take a reduced expression, and look at the braid, which is a positive lift of that element, and the functor corresponding to that. So for any W in the Weil group, and I think I didn't introduce this notation yet, so Weil group of G. Let's take a reduced expression. And then, and beta is the positive lift in the braid group. So then we have the functor theta sub beta, or maybe I'll stick to writing W, sorry, but really I mean this is now a braiding functor, which is just the composition of these individual ones. Okay, so now that I've introduced the Ricard complexes, let me tell you about perverse equivalences. And then, well, I'll make the claim. I was going to say a little bit about the proof, but I think maybe I'll answer questions about that after, just so I can say more about the second project as well. So let me tell you a little bit about what this structure is, these perverse equivalences. So as I mentioned, part of the problem was we had this element S that we wanted to categorify, well, that Chang and Ricky categorified. Because it's an alternating sum, it can't be done in a straightforward way just on the category C. We need to work on complexes. Now, working on the level of the bounded derived category, there's still a way to recover back the original underlying abelian category C with this kind of structure. So given two abelian categories, C and C prime, and those are, so I'm going to describe it in general, but specifically want to apply it to the categorification setting here. So a derived equivalence so F from dBc to dBc prime. So remember, or if you haven't seen derived categories before, maybe here for the first time. So roughly speaking, what is this? We're taking complexes in C, co-chain complexes, up to chain homotopy, and by inverting quasi-isomorphisms, so maps which are isomorphisms when we take cohomology. So if you've seen derived categories before, this is a quick reminder. If you haven't, this is a lightning introduction. But for the level of this talk, really, we're just thinking about complexes up to further identifications, right? So such an equivalence is perverse with respect to some data. So that data includes two filtrations, one on C and one on C prime, as well as the perversity function P. So where C dot is just a filtration by Serre subcategories. So let me, C0 is going to be my first index up to Cm, and C prime similarly. So with the same indexing set, C prime, as well as a perversity function which maps from 0, 1 up to m to the integers. So this is the data with respect to which our functor is perverse. And this is true if, so the first property is that f, so shifted by this value at the ith level determined by this perversity function. So we're thinking about complexes here. So this is just a homological shift, shifting the complex by some amount to the left or to the right. So this is some homological shift. This gives us an equivalence on certain subcategories. So let me explain what those are in a moment. So as I mentioned, we're thinking about complexes. We can compute their cohomology. And here we're taking the ones whose cohomology is concentrated in this subcategory Ci. So in general, it's going to live in C. But now we wanted to live the cohomology of the given complex to live in Ci. And similarly on the other side in Ci prime. So these categories actually give us filtrations on the derived level as well. And essentially we want this functor to preserve these filtrations up to some shift of the complex. Okay. If nothing else, at least hopefully you'll get some idea of what a perverse equivalence is in this language. So this is the first property. And the second one is, as I mentioned, that it recovers the original underlying abelian categories. So then we can take the associated grades, so in particular on successive quotients here. We still get an equivalence. Sorry, these are C prime. But this induces an equivalence on the underlying abelian category. So this is the additional requirement. So the first part is telling us that this functor is roughly upper triangularizable with respect to this filtration. So that's a nice property to have. And the second one is that it induces an equivalence on the underlying abelian level. So this is the structure we're interested in. And as I mentioned, one of the things we were able to show in the first project is that these Ricard complexes, when you consider the ones corresponding to W naught P, so long as parabolic elements, they have this particular structure. So maybe let me give that as that. So, and this generalizes a result of Chuang and Ruquier in the SL2 setting. But for the sake of time, let me mention our theorem and Chuang and Ruquier for SL2. C being a categorical UQG representation as before. So for any weight of C, and let me just mention it for W naught, but from here we can recover also all the parabolic versions. So longest element in W. So we get this factor, so this composition of Ricard complexes, which goes from dB C mu to the bounded derived category of the W naught mu weight subcategory. So this is a perverse equivalence. And I need to tell you what are the filtrations and what is the perversity function. So with respect to, so the underlying abelian categories, just like on the decategorified level, we have Jordan-Holder filtrations. So one can take the Jordan-Holder filtrations or a more coarse filtration given by the isotypic, the quotients being isotypic components. Either of these work for this structure. So with respect to a Jordan-Holder or isotypic filtrations. And the perversity function, so P of I, is given by negative, sorry, do I want plus or minus? No, I want plus, sorry. So the height of mu minus W naught applied to lambda I. So lambda I here is the highest weight for the ith quotient in the filtration. So where lambda I is highest weight for the Ci mod Ci minus 1 component in the filtration. Okay, and sorry, I'm already out of time. Can I spend a couple minutes talking about the second project? But this is the first project. So this is completed. You can find it on the archive if you're interested. Let me say just a few words about the second project, and I think I'll give you more of a schematic overview of that. And my student Erica will also be at the SL Math program next fall, so if you want to talk to her about that as well, you can find her there in the fall. So the version 2, so we have another diagrammatic algebra introduced by Webster called KLRW algebra. And maybe I'll just give you a few of the ingredients just to take a couple more minutes, and I will end it there. And then we're interested in taking the finite dimensional representations for this algebra. And it turns out that, so work of Webster tells us that this categorifies the tensor product of d lambda 1 up to d lambda n. Where each of these, so lambda bar is this n-tuple of dominant integral weights. From 1 to n. So any number of tensor factors. And so this algebra is again a diagrammatically defined algebra, where just to give you some idea of what it looks like, so we have n red strands labeled by lambda 1, so lambda I, lambda n, which are not allowed to cross each other, and then any combination of black strands with dots, just like we saw before, all of them are oriented down, and the black strands are labeled by simple roots. And again, subject to some relations, which I will suppress for the moment. So this is a finite dimensional algebra, maybe just, so finite dimensional, some properties. It's not, unfortunately, quasi-hereditary in general. It doesn't give us the highest weight category. So this is not a highest weight category, but it's standardly stratified, which is slightly weaker, but still a good property to have. And the braid action is what I'll finish with, just to tell you what that looks like. As I mentioned, it's tensoring with a certain bimodule. Unfortunately, that bimodule is not projective or flat. So if you tensor with that, it's not going to be exact. So it doesn't recover back the original R matrix on the Grothendieck group. So in order to fix that, we need to work on the derived level again. So we need to work on the so if I call this R, this category is R lambda, we need to work with the bounded derived category of that. So the gradient, again due to Webster, is so derived tensor product with, so each of the braids, let me call it beta I, is acting as the derived tensor product on bounded above derived category on R lambda to bounded above R SI lambda. And so this DI is again diagrammatically describable, where now we're allowing the red strands to cross, but only the I and I plus parts. And all of the other ones have to be non-crossing again, and we're allowed to have any combination of black strands in between them. So this type of module, again, subject to some relations, which I'll suppress for now. So it's very explicit and combinatorial diagrammatic description of this. And so our work in progress is to show that the functors corresponding to the half twists for this braid group action are also perverse equivalences, again with a Jordan-Holder filtration. So W naught is perverse with respect to a Jordan-Holder filtration. Okay, sorry for going over time, and thank you for your attention.
Maybe a couple quick questions. Okay.
I had a question about the first theorem. So, because at first the filtrations of the categories is like 60 integers, and then it becomes widths. Maybe I misunderstood something.
Sorry, I took the height. So when you express this in as a linear combination of simple roots, you just take their coefficients, and here we're working with integral weights throughout. So it's still an integer. Yeah.
So in this proposition by Kautys-Kapnitzer, what kind of geometries they use?
So they construct a geometrically defined categorical G action. They use derived categories of coherent sheaves. In particular, they work with cotangent bundles of partial flag varieties as one instance. But that, unfortunately restricts to the simply laced case. This is still expected to be true outside of simply laced, but it hasn't been proved algebraically yet. Yeah.
Again.